who will tell us something about how to call natively implemented functions from Erlang in a different way. In a better way, hopefully.
In a nifty way.
In a nifty way.
So, let's start by thanking the program committee of this year's workshop for a very enthusiastic set of reviews. It was strong accept, strong accept, accept. In contrast to the program committee of 2 years ago that actually rejected this paper for a totally ridiculous reason I will think about. It's the difference between hell and heaven, you know, it's, you know. So, so this is in, this is stuff in Erlang, and we are very happy to be in a heavenly place. This is supposed to be a Japanese garden in autumn. And here things are actually quite calm and nice. So all the calls in particular here that people are making are quite harmless and occasionally cute. So the calls here, you know, don't really cause any trouble. But there is a place called hell out there, and actually many people are susceptible to actually, the temptation to sin and to go there is actually quite high for some people. In particular, hell seems very popular out there. This is the data from 2014 on the popularity of languages. How much code is written in C and how much code is written in Erlang. You can see Erlang is infinitesimal compared to the amount of code that is written in C out there. Now, we definitely don't recommend people to go to hell or try that route. But the fact is actually that there is a lot of code out there that is written in C, and some of it actually works. So you probably want occasionally in your Erlang applications to interface with a library that somebody else has written in C. So this is the thing that we actually wanted to make easier to do from Erlang. We also had an ulterior motive here. We wanted to be using a property-based testing tool to be testing some applications that are actually written in C. So we needed to have a way of actually, and actually this were actually central network applications. So we needed a way to actually test some central network code that we had in another project. So rather than doing that sort of thing manually, we decided to write a tool that will automate this sort of thing, and then the tool became more and more mature to the point where we can actually release it to the other community as a component. So let's say that we actually want to call hell from heaven. You know, what are your options? The first option is to use a port driver. So to write a C program that connects C and Erlang using standard in, standard out, or you can have C nodes that use socket communication, or the more modern way, the so-called native implemented functions, or NIFs, and that's where the tool, the inspiration for the tool Nifty comes from. You know, the NIFs. So this is a shared library. Let's load the VM. It's a faster way. It's a more modern way. It's occasionally dangerous, of course. It can bring down your VM, or it can make the schedulers they don't give any fairness guarantees with the schedulers, and so you don't have the scheduling mechanism that you have in the Erlang VM. But let's say that you actually want to do that sort of thing from, for some reason, because you have it in your application, and let's say that you have a very small example. So you have a C function that you want to link in your application. Okay, so what would you have to write in Erlang to actually use this C function? So let's write here a NIF to translate the argument. Here it's an integer argument. Then we need to call this heaven function and then return the result. And let's see the code that one would have to write in Erlang for that. So you would have to start first of all writing in C. And you need to write this sort of thing for this heaven function. For each function that you want to use from Erlang, you need to write a C wrapper, this nif heaven here, that takes these arguments, and then it takes the argument here from argument 0 and puts it in some arg, and this might actually have an error, so you have to account for the case where you might have some wrong thingy here, and then of course you have to call the heaven function from C, and then you need to return the result, and the result happens to be integer here, so you have to write this code to start with. This is not all. Then you have to write some boilerplate here that says that, okay, now these are my set of nif functions, and I need to connect in Erlang the function heaven with arity1 with this C function, this C nif heaven. And then you have to write this type of thing, which is all my nif functions are in a demo file connected with the demo module, and actually you have to write these things. And if you want to upgrade or restart your application, you have to write other stuff here, not just null, 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 null. So most people actually write null, null, null because they don't bother about it, but if you actually have a real application, you need to write something to do upgrades and stuff like that. I don't even show you this. And then you have to start writing in a more heavenly language. You have to write your module, it exports your heaven. You have to write this init thingy that will be executed on load of this module. And finally you come to the heaven function in Erlang, where you have to write this amazing thing, Erlang nif error, nif library node loaded, and the Bing loader will do its magic when it finds this nif thingy and will connect stuff. So you have to write all these things just to call one C function that was just, depending on how you count, 3 lines of code or 2.5 lines of code, really, really small. So this is madness. Why do you really have to write all this stuff? So we wanted to, and actually it gets much worse, because if you want to do something more complex, then you have to write very complicated stuff. So we had an application here, a Snappy, that is a encoder, decoder, there's compression and decompression of some application. And there, you start seeing that actually things are a bit more complicated. First of all, you have some types that are not in this file. They are somewhere else. In particular, they are there. And then you have structures that might be used then afterwards in these functions. And you have to be able to understand what the structures are doing. And then, of course, you have pointers. And these pointers in C, they come in pairs that have now the length of this thingy in a different argument. It comes very much easily held, if you want to actually write these names correctly here by hand. So we wanted to automate this sort of thing, and I'll skip this. So let's automate this. So all the information here that we actually need is just given by one line. The prototype of the function, the declarations in the header files. So, and most of the time these are pretty simple. Okay, they are things that have the name of the function, what they return, and the arguments that this function is taking. Now, occasionally these things can be very, very, very complicated, like this one here. And a tool that is automatic actually needs to be able to handle this sort of thing. Otherwise, what do we support? I mean, C code is hell. What do you expect? So the return type here is a pointer to a function that returns in. It has a function pointer as argument. Don't even bother about this. So we did not want to do this sort of thing. We actually wanted to create this tool that called Nifty that takes a header file and produces automatically all the boilerplate that we need to write from by hand if we didn't have this tool. So how does this thing work? And here's the point where I do a demo. And let's keep this slide just to show you a demo. So is this visible, by the way? I cannot make it bigger. So, I have two files here, a demo.c and a demo.h. So the demo.h function has just two prototypes. The function heaven, that is the one I just showed you, and the function hell that I will show you shortly. Or actually, let me show it directly. So this is what they do. So heaven takes an integer x and adds 42 to it and returns it as a result. And the hell raises a segmentation fault. Okay, I do not want to write division like 0 or dereferencing a null pointer or whatever else. I just raise hell there. So using Nifty is very, very simple. You just fire up your Erlang shell and you write this thingy. Let me copy and paste it because I'm terrible. I type terribly. So you say Nifty compile. You take the header file, the demo.h. You give a name for the project, for the directory that you would like to generate all these things under. And you add all the sources, and you might have many C files. So this takes a list and takes some options. I'm not using any options at all. Okay, and this, you just press enter. This will generate, and it will generate two Erlang files, the demo.erl under SRC. So it makes a directory called demo, and under SRC it will create a demo.erl and a demo remote.erl. I will explain why we do that. And a C source with demo nif.c. It compiles the thing, and now it has actually loaded it also. So now I can write demo heaven with 0, and this will return 42 with some other number. It will return the number that you expect. Okay, so this is a real demo, it's not video. You can believe me that this thing works, at least for this example. Now, let's go back to the presentation. We saw this thing. So how is this under the hood? It has a parser, it has the generator of all the files, and it has a compiler. And you get back an if module and all the other stuff that you need to have in order to run this thing from Erlang. So let's start with a parser here. Do we want to implement the C parser? Absolutely not. We don't want to enter hell. So we use libclang. It's a widely available implementation of C compiler that is pretty good, and supposedly handles quite a lot of percentage of C out there. It provides it's a nice thing because it provides a high-level interface to the Clang compiler and gives us access to the abstract syntax tree and handles most of the arguments of C, at least most of the things that big projects out there are using. So we outsource this to libclang, and this is what we are using now. So this AST is processed into a type table and a symbol table, so we need to keep track of the types that are being used and also the symbols that are being used from this header file. So the types, we have a translation from all the C types to Erlang types, and actually Nifty gives you supporting routines so that you can actually refer to these things from Erlang. and you can refer to these types even if you actually want to from your Erlang application. So it handles all the base types of C, both C99 and more modern versions like things like Uint 64 or all the stuff that exists in modern C. It handles type defs that you might have in your header file and also user-defined types that you might declare. And the type table keeps information about the use types, like the specifiers, the pointers, the structs. And we need all this information for the Nif module generation and the use of the Nif module. So you can read the rest in the paper. I will not say more technical details about it, how this thing is implemented. All the code is actually there. I will show it at the end. Now, for the code generation part, we use early DTL that supports it's an Erlang interface to the Django template language, where we have templates like that we instantiate based on the use types that we have there and the variable names. So we generate all the stuff that the Nif file needs in order to be compiled. We generate all these directories, a C source directory where we have the C file that we need to write as a Nif, the bin directory where we put an app file and all the bin files that we can compile, from the source. And the source has two files, one file.erl and one file _remote.erl. And the include file is the HRL file that we generate for Erlang. And we also generated the rebar.config file. So I can show you all these things. Remember that we had only demo.h and demo.c in this directory. So if I do an ls here, it has a demo directory. And if I do an ls in the demo, this has generated a directory called c_source. And it bin and include the rebar config and a source. So for example, under C source, there is the demo nif.c, the demo nif.d file with dependencies, and the .o file. So all these things are automatically generated for you. Now, let's go to the very interesting stuff. So let's raise hell in the thing that we actually generated. And let's see what happens here. So as you remember, I also have a hell function that results in a segmentation fault. Let's try to call it here and see what will happen. So let's do this again. I can recompile, and now I can call demo heaven with 0. This works. And demo hell. And this will result in a segmentation fault. You don't want that, most likely. So you don't want to be running this code in the same VM. And this is exactly what the remote file is trying to do. So I can start again. I can compile again. And now I can say demo remote start. It gives you, and it started now another Erlang node where all the Nifs will run, or actually all the Nif functions that we want will run. And now I can call here, of course, demo heaven with 0. This runs on the local node. I can run demo remote heaven. This runs on the other node, but this one is the heavenly function, so it's not a problem. And I can write demo hell here that will bring down the other node, but this node, of course, still is up and running. And now of course, I can design my application so that it restarts the application. There is a restart function also that you get for free. And this now runs and creates another node, and then I can run Heaven again, and it works. So you get all this infrastructure by Nifty. We also have support for dirty schedulers. To use it is very, very simple. You just say, I want to use the dirty schedulers as an option in the compiler. And this enables dirty schedulers for all functions of the module. You can actually use it for only some of the functions. But I will not show you how this is done here in the manual. So this will enable dirty scheduler support, provided of course that your OTP is configured with dirty schedulers. This is not by default in recent versions. This is exactly the reason why this paper was not accepted 2 years ago, because we didn't have support for dirty schedulers. This was something that was not even in the main on GitHub in Erlang OTP back then. So I don't understand how people can ask a tool like that to provide support for something that doesn't even exist. Anyway, enough rambling. Now another option here, if you don't want to use the schedulers, is to, and you are afraid that perhaps your NIFs will occupy schedulers, is to use the remote facility that we have. So of course these tools comes with some limitations. We don't support anonymous structs and unions. And nested structures are now automatically rewritten. So this is not a limitation that we do that sort of thing automatically. We don't, function pointers are the same to void star. And this is not actually elimination of Nifty. There's no support currently in the Nifty library for Erlang OTP to call Erlang function from C. So you cannot have that sort of thing. And variable argument lists, we only support the ... notation. The VA list, the variable argument list notation of C cannot, we don't generate wrappers for that sort of thing. So we have actually used that thing. We have some experience. We have taken some libraries that are out there. So one library we played with is 0MQ. It's a messaging library written in C. It contains 35 plus change lines of C and C++ code. Its header file has 416 lines for 45 exported functions. And Nifty just processes this out of the box and generates a NIF file of about 4,000 lines of code. You probably don't want to write this by hand. We did not want to write this by hand. And everything works. All the examples we tried work. So this is some sign that this is a robust tool out there. Also, we did the same thing for Modgoose. Is a web server. It's smaller than the other one, but still the NIF file is of considerable size. For this case, we need to provide some event handling callbacks, of course, that cannot be generated automatically. Now, we also have some more experiences of our own interest. We have used this for testing sensor networks, and there it was actually more challenging because we had to interface with an operating system, the Contiki operating system. This is an architecture that is slightly, I wouldn't say exotic, but not really your average laptop that you have. And we have a paper for anybody who's interested in finding out our experiences there. That's pretty much about it. The Nifty tool is available on GitHub, and it already has some small user base of about 100 starred users, but more feedback is welcome, and of course contributions or in the form of support for new features or things that you would like to have in your environment and you don't know about. That's about it.
Could you please go back to your slide where you showed the examples, the tools where you've experienced?
This one?
Yes. So you've said that you generated, I don't know how many, more than 3,000 lines of code. Do you have a handwritten version of that as well, or it was just a C library and you tried to generate the Erlang interface for that? So is it used by somebody from Erlang? So these functions were already called from Erlang with a handwritten code, or you just picked up this library and tried to generate it?
This is just an experiment where we picked up a library and tried to generate it, and then we used it from Erlang. We used it. Now,
So
whether somebody else uses it from Erlang, I don't know, but we used it, and we ran all the examples in the tutorial.
Okay.
So it actually works. The examples, at least in the tutorial, perhaps other stuff that I mean, we are not a 0MQ user. We just wanted to try this to see actually whether we can handle a big code base out there that, and what we generate is correct. I think it is correct, but you never know.
Okay.
So we are using some version of this 0MQ in our work. I was wondering whether it's the same, the version generated by you or not. Is it available on GitHub, your versions?
We don't have any available 0MQ version. We have the Nifty tool that
Yeah.
you can download, and you can use whatever version of 0MQ library you want, and you will get all the code that you need to have in order to use 0MQ from Erlang.
Yeah, so I mean, we are already using some Nif version available online, open source. So I don't know I don't remember who wrote that, but yeah.
I think so. There is maybe you can compare now. You know, so they have implemented the bracket functions by hand for 0MQ, and you have generated one.
Yes. So besides, us doing less work, I also would very much recommend using Nifty or something like that, because now you can get a new version, and perhaps there are some new functions that you can use, which otherwise you would have to write by hand. And I would not want to do that if I were you, but... Yes, Laura?
It surprises me that the number of lines that are generated in both cases are kind of in the same order of magnitude, even though the number of lines...
No, the number of lines actually not particularly interesting. What is interesting is that you have 45 functions here and 30 functions there. But this very much depends on how many arguments these functions have, because you have, one line and stuff per argument, and if the types are more... So this is actually not, this is just a surprise, to just impress my mother, that I can handle that many lines of code, but actually all that Nifty does is it handles the 416 versus 146 lines of code. Yes?
So there are foreign function interfaces for many, many languages, and most of them are to C, because C is the lingua franca. Can you characterize the difference between Nifty and some of these other FFI capabilities for other languages?
Okay, that's a very good question. Of course, in the paper there is a section on related work and stuff like that that you are welcome to read on the way back. I guarantee you it will put you to sleep. on the way back. But there is very little information actually published on how similar tools to Nifty work. There's a lot of information about foreign language interfaces of languages, but I have not seen many published works for tools that take a header file in C and generate all the boilerplate that you need to call it from, say, Haskell or... Now, this might just say something about the literature I've seen. So, for example, Cubic had something similar to generate some interface to C functions so that they tested from Quicksort. But I don't think you have ever published this or even described this, let alone distribute this. I don't really know how these things are implemented. It's quite likely that they are very, very similar. But I have not seen that many published books. I've seen a lot of published books about the foreign language interfaces, but not generating this stuff automatically. Perhaps John might know more about this.
So, if we look at Haskell, there was a tool called Green Card many years ago, which took something like header files and generated interface. And that's been replaced in more recent years by the foreign functional space that is now built into Haskell. Green Card was trying to do things like distinguish between pointers that are input parameters and are output parameters, and take into account things like you have a pointer and a length, and you're supposed to interpret it as an array. So there's a lot of interpretation of C APIs, but information that isn't in the header file. And I think there's been, certainly where Haskell's been concerned, there's been some doubt about how much to try and automate those interpretations. I take it that if you return a pointer
Yes.
from a function, you just return a pointer.
So this is an example where this is an input,
Yeah.
and it has the length of the input, and this is the output one where the compressed message will be returned,
Yeah.
and this is the length of the compressed. So we need to do something similar there.
Right. So you don't know that, or the tool doesn't know.
No, the tool doesn't know that at all.
It's up to the user to then do something appropriate.
Yes, but the user doesn't need to do anything about the C function. It has to do with what it will do from its application to call the wrapper of this function.
Right. You have to write a wrapper
Yes,
that knows that
of course.
input is an input parameter and compressed is an output.
We cannot write your application automatically, unfortunately, yet.
So there's a language called IDL, Interface Definition Language, from which these kind of things have been generated, and that attempts to provide more information about how these parameters are intended to be interpreted.
So we initially wrote Nifty for our own users, but it became to the point where it was actually, we thought it would be useful for other people, so we decided to release it and also write it about it. So it's not a very deep thingy, but I think it's very handy, Nifty.
I have just short about the runtime. So how fast is it? So of course it's faster than write it by hand.
No, it's
but-
very, very fast.
So it's
I mean, it's really
just seconds or
even less. I mean, it's just,
okay.
I mean, it's part of the compiler. I mean, you saw it here. Of course, it was a small file, but even in this big applications, it's
Okay, but you
really
have to
a
call
compile.
Clang and
No, we
I
did.
don't know how fast Clang is, so for parsing. But okay, so it's fast.
It's pretty fast. This is not going to be the trouble that you might have at all. I mean, it's so fast that you actually don't even need to store the generated file. You can generate them